All right, so we just sort of explained why this theorem 3.4 is true and what lemma 3.3 has to do with that by way of these examples. Let's look at another example here where we want to find the determinant of this matrix. Now, this is definitely not an upper triangular matrix because these are non-zero here, and it's not a lower triangular matrix because these are non-zero here, but this is a non-invertible matrix. We do have linearly dependent columns because if you do column 1 plus column 2, you'll get column 3. So how can we use that to see what the determinant is? Well, first of all, let's make a guess. What does your intuition say the determinant of A should be given this situation with the columns? And pause it because I'm about to tell you the answer. The answer is that it should be 0 for some of the reasons we were saying before about volume, that like if you're going to draw the parallelepiped in 3 dimensions with these, the third one doesn't contribute any volume because it's like in the same plane as the other ones. So the parallelepiped is just like a hexagon thing that maybe looks like it's 3-dimensional, but it's like the situation on your screen right now. Like your screen is literally a 2-dimensional thing with 0 thickness, and this is in that screen, so it has 0 volume. So let's actually try to calculate this determinant. And the goal is to show that it's going to be 0 using lemma 3.2. We're going to try to reduce this using column multiplicity placement to get a column of all zeros. So first I'm going to replace column 3 with the sum of itself and the opposite of column 1. Wait, you can't do that. That's not technically a operation. So we can do the opposite of column 1 and column 3 to replace column 3. What I was thinking is we could do this, but that would be combining it with like a scaling operation, and we're not doing that. So yeah, this is going to be 2 minus 3, which is -1 here, and 4 minus 4 is 0, and -5 plus 3 is 2. And now we're going to do the same thing with column 2. The opposite of column 2 plus column 3 to replace column 3. Like so, and at this point, we know this is going to be 0 using lemma 3.2 that says if you have a square matrix with 0 in a column, its determinant is 0. Okay, so this is all sort of trying to justify theorem 3.5 here with some examples, that if you have a square matrix that is not invertible, well, by the way, how do we know that this makes it not invertible? If one of the columns is a linear combination of the other, that means the columns are linearly dependent. And looking back at the invertible matrix theorem here, if you have linearly dependent columns, your matrix is not invertible. Likewise, example 3 was another situation where you have linearly dependent columns and this is a not invertible matrix. There's no way to get this to be equivalent to the identity. And that also had determinant 0. Now this says this works in general, that the determinant is not 0 if and only if A is invertible. So just a little warning, this proof is going to be kind of technical. It's an important enough theorem that we're going to use in 3.2 a lot that I feel like I want to have enough mathematical rigor in this course that we're going to include it. But if you zone out for a little bit, this is an okay place to do it because this theorem is going to be a little technical. But yeah, let's prove this theorem. we're going to let B transpose be the reduced row echelon form of A transpose. We know we can do that because A transpose is a matrix. Every matrix can be row reduced to reduced row echelon form. And there's a sequence of row operations that do that. Let's think about those row operations. They could be row multiplacements. They could be row swaps. And they could be row scaling. And scaling a row always has to be done with a non-zero scalar to be a Gaussian elimination legit row operation. Now, each one of these corresponds with a column operation that you could do to transform A to B. Like whatever you're doing with rows of A transpose, the rows of A transpose are columns of B. So there's a correspondence here with doing the same column operations that make A column equivalent to B. So column operations that you could do one at a time with A that result in B. Now, these column multiplacements and column swaps and scaling, let's think about how these all change the determinant. Column multiplacements don't change the determinant at all. Column swaps, we saw with the anti-symmetry theorem, multiply the determinant by -1. Column scaling, using the linearity property, multiplies the new determinant by whatever the non-zero scalar is. Okay, so whatever the column operations are that make A column equivalent to B, where B is the transpose of a row reduced echelon form matrix, these column operations are all multiplying the determinant of A by a non-zero scalar. So when you do a sequence of them, you're just multiplying the determinant of A by a sequence of non-zero scalars. So the product of all of these non-zero scalars, when you multiply them all together, is going to be this thing K, which is not 0. Okay, at this point, we're ready to start actually talking about the parts of the theorem that relate the determinant of A being 0 or not to A being invertible. So the first thing I want to do is notice that this equation implies that the determinant of A is not 0 if and only if the determinant of B is not 0. We're going to have a chain of equivalent statements here and try to connect it to the fact that A is invertible is the goal. Now, why do we have this fact? Well, because if A is 0, then this non-zero number times B will be 0. And if B is 0, then the determinant of A is 0 divided by K, which is non-zero. So, yeah. Now, the determinant of B is not 0 if and only if this next statement is true, which is that B is equal to the identity matrix. Now, let's talk about why that is. We can justify this over here. First of all, if B is the identity matrix, then certainly the determinant of b is equal to 1. That's the normality condition, and 1 is not 0. Okay, what if b is not the identity matrix? Well, that means that B transpose is not the identity matrix, and B transpose is a reduced row echelon form matrix, and it's square, so that means it must have a row of all zeros. And if B transpose has a row of zeros, B has a column of all zeros, and that makes its determinant 0. So this step is really why we're talking about reducing A transpose to reduced row echelon form, because we know that a reduced row echelon matrix that is square and isn't the identity must have a row of all zeros. Okay, now at this point, if B is the identity matrix, that's true if and only if B transpose is the identity matrix, and that's true if and only if A transpose is row equivalent to the identity matrix, which means A transpose is invertible using the invertible matrix theorem. And using a different theorem from chapter 2, that is true if and only if A is invertible. So, yeah, we have connected the fact that the determinant is not equal to 0 with the fact that A is invertible by way of the reduced echelon form of A transpose, because row reducing A transpose is the same thing as column reducing A, and we know how those column operations affect the determinant. So yeah, that proves the theorem. Pretty technical, but that is going to be important for the other theorems that we use in section 3.2. So yeah, we have a lot here. The homework is partially using these properties, the definition and theorem 3.1, to like do the column reductions to get a triangular matrix, which tells you what the determinant is. There's also another important theorem you're going to have to prove as homework. So good luck with all that, and I will see you later.